Good morning, class. We continue our lesson. Still on discussing the missing link of quantum dot solar cell. We will discuss the missing link number 2, which nobody has ever studied this before, which is the absorption cross section. The absorption cross section is referring to the absorption spectra of the quantum dots. If we compare the absorption spectra of quantum dots with the dye, so what are the differences? So this is the question. The quantum dot solar cell and dye sensitized solar cells, they share the same device structure. Sekejap. Going to use the mic. So the question is why the DSSC performs better than QDSC even though they have similar device structure. The only difference is that in QDSC we replace the dye with our QDs, and furthermore QD promises high theoretical efficiency, more than 60%. However, the real device of QDSC is not at the par with the DSSC. The best performing DSSC is, what is the percentage? 11 point something. How about QDSC? Lower than that. So we need to find out. So the missing link number 2, as I mentioned before, we need to study the absorption cross section by referring to the absorption spectra. So this is what I have done before. I have compared the absorption spectra of dye. So the dye that I have used is the N3 dye. This is the best performing dye for DSSC, which is the name is N3 dye. The size of the dye also has been recorded. F is oscillator strength. I'll explain to you what is oscillator strength. Alpha A is the absorption cross section. And I have simulated 4 clusters of quantum dots, which is CDSC. CDSC 6, 13, 16 and 26, and the sizes also recorded over here. They have different sizes. And so let's take a look at this graph. So what can we see? We have 2 y-axis. We have 1 x-axis and 2 y-axis. This y-axis is the extinction coefficient, which the symbol is epsilon. And that y-axis is the oscillator strength, and the symbol is F in the unit of dBi. So what are the differences? Oscillator strength is the ability, how strong does your dye or your material oscillates when they absorb the energy of light. Before excitation happen, for example, if your dye absorb sunlight with sufficient energy, before the electron excite to the LUMO, they will vibrate first, and the strength of this vibration is called the oscillator strength. They vibrate and they receive energy. Until the energy is high enough, they will excite. That is oscillator strength. How strong does your molecules or your electrons in the molecules vibrates when they absorb the energy of the sunlight? So if you refer to the value of F over here, it looks like our CDSC 26 vibrates, the electrons in the series 26 vibrate stronger than the other clusters. And the electron in the N3 dye vibrates the lowest. And how about this axis? The extinction coefficient. Extinction coefficient is that how strong your material will absorb the sunlight. This one, how strong is the electron in your material vibrates when they absorb sunlight. And that axis indicates that how strong your material can absorb sunlight. So this y-axis is referring to the vertical lines. These vertical lines indicates the oscillator strength. See, this is the dye, the blue curve over here. This is the straight line. A, entry die, F 0.056. It has the lowest oscillator strength if we compare to all the other vertical lines. And the extinction coefficient, that y-axis, is referring to the pinnacle top of each curve. So for example, the blue one, the pinnacle top is this one, about 2 point something, not recorded over here. Okay. And the others, for example, the purple line, the extinction coefficient is this one, 7 point something. So it shows that the quantum dots has higher ability to absorb sunlight if we compare to dye. So when we look at these two y-axes, it appears that the quantum dots is superior than the dye. However, the efficiency of quantum dot solar cell is still lower than the dye sensitized solar cell. So this is the wrong way of observing phenomena. It seems that the oscillator strength and the extinction coefficient is not the correct point of view if we want to analyze DSSC versus QDSC. So we need new angle. These two y-axes cannot tell us the correlation between the inferior properties of QDSC if we compare to the DSSC. From these two axes, it shows that our quantum dot is the best, but we cannot correlate between these two properties with the poor performance of quantum dot solar cell. That is why we need the other angle, which we need to look from the alpha A. Alpha A is the absorption cross section, the area under the graph. So if we calculate the area under the graph, meaning that we have to integrate to find the area under the graph. We could use integration using microcal origin very easily. This is how I get this value using integration function in the origin. So the area under the graph for the entry die is 1596.28, and if we compare with the other area under the graph, it clearly shows that the entry die shows the best. So this is the reason we need to look from the area under the graph. So the area under the graph indicates that how many electrons could be excited upon absorption of photon. Just like what I've told you in the chapter 1, the first excitonic peak is very important. So this oscillator strength also indicates our first excitonic peak. If the first excitonic peak is at the long wavelength, it means that our material could be a good potential for solar cell. So when the first excitonic peak is on your right hand side over here, it indicates that it could absorb light with the lowest energy to initiate electron excitation and keep on exciting more and more electron when light with high energy is exposed to your material. So in chapter 1, I have explained very briefly. So this one in detail, it's absorption cross section. Not just the height of the peak is important, but the width of light absorption is also important. So that is why the entry die could yield about 10.4% of photovoltaic conversion efficiency. If we compare with the other CDSE 6 and until 26, they only produce very low efficiency. So now the challenge is that we need to synthesize quantum dot which has higher alpha A than the entry die. Okay, this is how we read. I have mentioned how we read the F and how we read the epsilon. So can we increase the absorption cross section of the QDs? This is the challenge. It is proven that the width I mean the alpha A is important, and the QDs, they have very low alpha A. So can we increase the absorption cross-section or the alpha A of the QDs? Yes, we can, of course. This will lead to missing link number 3, which also leads to the problem of size distribution effect. So how do we widen our absorption cross-section? Now we could use this method. Somebody already done that by Kunkanan. I think this guy is from Thailand in 2008. He presented his work in Journal of American Chemical Society. However, his effort exactly could widen the absorption cross-section. However, his device only shows less than 1% of photovoltaic conversion efficiency. So what he did was he used different sizes of quantum dots. For example, he uses 1.5 nanometer of CDSE until 2.4 nanometer of CDSE. What was his idea? Okay, 1.5 nanometer CDSE, it has this much of band gap, and this much of band gap, they absorb intensely photon at 500 nanometer. And he combined this 1.5 nanometer with the 1.9 nanometer quantum dots. And this quantum dot could absorb light very intensely at 530, so on and so forth. He uses different sizes. And each size of quantum dot, they absorb different wavelength. Cumulatively, he could absorb very wide wavelength of light. And his device called as rainbow solar cell. So the base will be the base, meaning that the quantum dot that will attach to the TiO2 will be the biggest quantum dot, followed by the second biggest, third biggest, fourth biggest, so on and so forth. So he got something like a needle, which in the base of the needle is the big quantum dot, followed by the smaller, and the smallest will be the tip of the quantum dot. So it is a rainbow type quantum dot solar cell. Why rainbow? Because each size of quantum dot, they absorb light with different wavelength. This different color. All the quantum dots are absorbing different color. So if the absorption cross-section already been widened, why does he only got less than 1% of efficiency? So the story is like this. Back to the energy level alignment. These are the energy level alignment. I mean, this guy doesn't know the drawback of his device. And the drawback of his device was revealed by my team. We have this much of energy level. If we align them, it shows that we have drawback over here. This size is the problem. It has lower LUMO than the conduction band of TiO2. How is the electron going to be injected over there? This is energy level misalignment. Plus, this is not good. Electron will be excited at each quantum dots separately. However, this excited state electron will be injected to the neighboring electron, to the neighboring component, and injected to the neighboring component and neighboring component. This mechanism is not good. This will slow the electron injection. We want fast electron injection, meaning that from the quantum dot direct to the TiO2. We want that. This is slowed electron injection, not good. ISC will be lowered. When IC is lowered, of course, your efficiency will be lowered as well. So this is drawback of his device. Okay, if this quantum dot is not good and electron injection could not happen, why does he still got small amount of efficiency? Meaning that certain electron could be injected. Why? So back to the question again. The ability of human being to control nano reaction in the device, we cannot control. We are not God. We cannot control. We just could claim that, okay, these quantum dots could be stacked up simultaneously. The first layer, second layer, third layer, and fourth layer. We just assume. Most of the material will arrange themselves in that mode. However, we need to remember, we cannot control every reaction, including the nano reaction. Maybe, this is just assumption, not hypothesis but speculation. This quantum dot, some of the space that attached to this TiO2 does not involve this quantum dot, only involve these 3 quantum dots and giving electron injection from here to there. And due to the slow injection, we only got 1%. Understand? Remember, we cannot control reaction. This is the best reaction could happen, but sometimes it doesn't happen just like we assume. Maybe this quantum dot doesn't participate in the reaction. So the rainbow type quantum dot is exclusive of this quantum dot. Only got these 3 main components and give us some photovoltaic conversion efficiency. Now somebody might ask, the poor performance of the QD-SC could be due to poor absorption of QD. The QD doesn't attach properly to the TiO2 or the MOS, metal oxide semiconductor. So can we mimic the way dye is absorbed onto the MOS? Can we somehow manipulate other chemical to attach the quantum dots onto the TiO2? The difference with our dye and our quantum dot is that dye has functional groups. They have carboxylic, they have what else? Mercaptan, the SH and also the COH. But our quantum dots don't have that COH or SH. So can we mimic the way dye is absorbed onto the MOS? Yes, we can. This will be the missing link number 4, which is the ligand effect. Ligand. This is an example. This is our quantum dot, the CDSC, the best performing CDSC, which is CDSC 13. And we attach our quantum dot with ligand, and this ligand is let me see, mercaptoacetic acid. This is the structure of mercaptoacetic acid. And we have mercaptan functional group over here. SH is mercaptan. And we have COH over here, carboxylic. And the carboxylic group attached to our quantum dots. And the mercaptan over here will be attached onto the TiO2. This mercaptan will be attached to TiO2. So our quantum dot will attach strongly to our TiO2. Somebody has published this, Sun, in 2010. He successfully attached the mercaptoacetic acid onto the CDSC, and this conjugate is attached strongly onto the TiO2. So how many percent? He only got 0.66%. Another failure. What is the problem? The problem lies over here, because energy level misalignment. So we want to attach CDSC with the mercaptoacetic acid, and then mercaptoacetic acid will be attached onto the TiO2. So electron movement, the excited state electron movement should be start from here, injected to mercaptoacetic acid, but that doesn't happen. Why? Because the energy level is not suitable. The LUMO of mercaptoacetic acid is higher than LUMO of CDSC13. No electron could be injected. So if 0% electron could be injected, why do we still get 0.66%? As I mentioned before, if we can't control the macro reaction, how can we control the nano reaction? Some of the CDSC doesn't attach onto the mercaptoacetic acid. Instead, it attached directly to TiO2. But mostly the quantum dot attached to mercaptoacetic acid, which give us very low efficiency. So he also tries different mercaptan, different ligand, and this time he tries mercaptopropionic acid. This is MPA, mercaptopropionic acid. Another failure. He only got 0.41% because energy level misalignment. So in conclusion, we could use the ligand to make sure our quantum dots will be attached onto MOS strongly. But we need to find the most suitable ligand which has energy level suitable with our quantum dots and also with our TiO2. MAA and MPA is not suitable for our CDSE quantum dots only. For other type of quantum dots, maybe if the LUMO of quantum dots is higher than LUMO of mercaptan, we could use them as our ligand. MAA and MPA not suitable for CDSE quantum dots only because of energy level misalignment. If we have other type of quantum dots with LUMO higher than LUMO of MAA or MPA, we could use them. And MAA and MPA is suitable for TiO2 because TiO2 energy level is over here for 0.2. So it is suitable because electron has to be injected from the mercaptan to the TiO2. MAA and MPA is suitable for TiO2 but not suitable for CDSE. So we need to find other type of quantum dots if we want to use TiO2 and these mercaptans, MPA and also MAA. So another point is that how does the electrolyte affecting the electron regeneration in quantum dots? This will be missing link number 5. Nobody has studied the redox potential of electrolyte, so we need to take a look at that. This is the ideal mechanism in quantum dot solar cell. Ideal mechanism. See, this is our CDSE 13, the best performing CDSE quantum dots. It has this LUMO and HOMO, and the LUMO is compatible with TiO2. The LUMO of quantum dots is higher than conduction band of TiO2, such that electron will be injected. The excited state electron will be injected to the conduction band of TiO2 and extracted out from the external circuit and back to the HOMO of CDSE using the redox potential of electrolyte. So the redox potential of electrolyte needs to be higher than the HOMO of CDSE 13 so that the flow will continuously happen. So I have chosen one standard electrolyte that widely used in the quantum dot solar cell research, which is the ionic BM2. This is the structure of the electrolyte. So from this structure, I could simulate and calculate the redox potential of electrolyte. It happens that if this is the ideal redox potential, ionic BM2, the redox potential is this much, this high, which prevents from efficient electron regeneration to HOMO. It prevents electron from going back to HOMO. So let us take a look. Upon absorption of sunlight, this electron will be excited to LUMO of quantum dots, and this electron will be injected to the conduction band of TiO2 over here to be injected, and this electron needs to be channeled up from the external circuit. This is the redox potential of electrolyte. I change the location over here to make you easier to observe. It go through the external circuit and go to the electrolyte. Sebenarnya ni sama je lah. Saya alihkan sini for easy observation. It needs to go through the redox potential of electrolyte. The best performing redox potential of electrolyte should be lower than the LUMO of quantum dots. But how about this redox potential? It is even higher than the LUMO. So this electron could not be injected to our electrolyte. The electron stops here. And if the electron would not go inside our electrolyte, how come this electron could be regenerated into our HOMO? So this is the drawback of the device, and he got very small photovoltaic conversion efficiency, about 0.3% in this device. Another failure. So if no electron could be injected, how can we still get 0.3%? As I mentioned before, we cannot control the nano reaction. Something might happen somewhere inside this device structure. Now we could speculate that this 0.3% comes from here. Instead of this electron injected into the electrolyte, it could bypass the electrolyte and injected directly into HOMO. However, the percentage of that injection is very low, which contribute to 0.3% only. Understand? Understand? No? No? Don't understand? The discussion today is all about energy level alignment only. We just need to see the energy level alignment. This is the ideal one, but the real one is this one. Nobody has studied this. This is the real one. Everybody is expecting the mechanisms like this, just expecting without any proof. So we prove them scientifically. This is why your device is wrong. This is why you got only 0.3% because your electrolyte is not suitable. Instead of this one, the level goes up to that point where electron could not be injected to a higher energy level. Electron needs to be injected to the lower energy level. Dan ini, this electron will be injected here ataupun ke sana lah. Saya lukis sini supaya senang nak tengok. Will be injected to lower energy level. This one, the redox potential is higher. Electron cannot be injected to higher energy level.
I have a question. Based on figure A, the electron from the conduction band on TiO2 you inject to the PT, right? And then to the electrolyte. For the P also, right? PT to electrolyte. So not from the TiO2 to electrolyte.
Yes. Same case. If electron is injected to PT, cannot go anywhere. Still, it needs to be injected. I mean, to be regenerated to HOMO, it needs to go through the electrolyte. Without going through the electrolyte, we cannot get. Even though if this electron could be injected to PT, it cannot be injected to electrolyte. It will diminish over here. Habis recombine at PT. Still, we need the electrolyte. Inject to PT, cannot go up. Then cannot be regenerated over here. Same case. Question? No? Okay. These are the type of conjugate fabrication. If we have solved the problem of the quantum dots and the electrolyte. So let's say we want to fabricate the quantum dot attached onto the surface of TiO2. We have these 5 procedures. We have the first one, organometallic procedure, or we name it as OM. We have the second one is successive ionic liquid absorption and reaction, or SILA. We have chemical bath deposition, or CBD, ligand assistance, LA, and direct attachment, DA. This is without ligand, this is with ligand, this is without ligand, and also without ligand. Let's see the figure over here. These are the TiO2, or the metal oxide semiconductor, which we have fabricated using hydrothermal method. And the structure is nanorods with a length of about 1 micrometer, and the width, diameter of the nanorod is about 200 nanometer. So this is bare TiO2, freshly fabricated TiO2, and we use organometallic procedure to absorb our CDAC quantum dots onto the surface of TiO2. This is before, this is after. Can we see the CDC quantum dots? No, because the CDC quantum dots is too small. This length, this scale is about 200 nanometer. If we want to see 2 nanometer, we have to divide this scale about 100 times, and we cannot see even one dot of the CDC over here. Cannot see, looks like no difference, but the CDC is there, confirmed by the XRT and also the TEM. This is using organometallic root. And how about if you use Scylla root? Scylla is very easy. The name is very lengthy. Successive ionic liquid absorption and reaction. Scylla. The thing is that we just immerse. Just like you immerse your TiO2 inside the dye solution, right? So we have few beakers. We want to produce CDSC quantum dots onto the MOS. So first we dip our TiO2, the glass coated, the TiO2 coated glass into the cadmium salt precursor, cadmium salt solution. Then we dip for a few minutes in ethanol. Then we dip into the third beaker, which contains the selenium salt, and we dip into the ethanol. Then we got CDSC produced onto the surface of our MOS. We repeat that cycle for a few times. Then finally we got full absorption of CDSC quantum dots onto our MOS. Just dipping technique, simple technique, but the name is lengthy. So this is before we got nanorods of TiO2, and this is after. So the quite thick. The diameter of TiO2 is about 35 nanometer, and the thickness of CDSC is about 21.36 nanometer. Is this quantum dot? The diameter of TiO2 nanorod is 35.68 nanometer. After the Scylla procedure, the thickness of CDSC is 21.36 nanometer. Can we consider this one as quantum dot? No? Let me tell you one thing. We cannot jump into conclusion using this image only. If you want to know the question, I'm fabricating quantum dot solar cell. I have to make sure that my CDSC in the region of quantum dots. From this image, I could see that the thickness of CDSC is 21.36 nanometer. And I know that the exciton Bohr radius for CDSC is about 4.9 nanometer. Looks like this is not quantum dot, but I have to check. How to check? We go to the so many procedure. We can go to the XRD, and we also could go to the absorption spectrometer. From the absorption spectrometer, first we need to synthesize CDSC, which is equivalent to CDSC 13. It shows this graph. And then we do the Scylla procedure. We got this structure, and we record the absorption spectrometer for this structure, and we got something like this, nearly similar. This is quantum dots only. The red one is quantum dot onto our TiO2, and the graph looks like very similar. We could conclude that, oh yes, in that case, even though the size recorded over here is very big, but the particle that make this thickness is the same small particle of CDSC 13. Macam mana? Macam ni. Sebab saya dah contek. Let's say one dot is the size of our quantum dot. This is about 2 to nanometer. And this thick of CDSC material is actually made out of very small dot of our quantum dots. Then we check with UVBs. We got this graph, meaning that this dot will give us the black line. Bare dot, one dot only. This is bare QD. Only QD give us the black line. Ni kan? And this one, the QD that is accumulated onto the surface of TiO2, we check, it gives us the red line. And these two graphs nearly similar, and we could assume that they are similar. Nearly similar. Only small shift of the peak. We could conclude that this CDSC13 that already been attached onto the TiO2 is the same CDSC13 with the size of this dot. Now if the quantum dots inside the TiO2 CDSC conjugate give us different graph, for example, remember the bare quantum dot is the black one. If our quantum dot in this structure give us this line, see the difference? Very big difference, and they are not the same. And the size definitely different. Each size of quantum dots or material, they will give us different position of peak. When the peak is shifted to the right hand side, it means that the size of our material is big. So this is how we confirm our observation using UV spectrometer. We have so many other techniques, but this is one of the techniques. We confirm the size of the quantum dot using the absorption spectrometer. Same goes for this one. Okay, the presence of this CDSC could be confirmed by the absorption spectrometer. If the bare quantum dots, the graph of bare quantum dots coincide with the graph of the quantum dot TiO2 conjugate, we could confirm the presence of CDSC. Now, missing link number 6, electron injection efficiency from quantum dots to MOS. Hey, time's up. Ada kelas tak? Tak ada. We continue next week.